last we finished off talking about the structure of magnetic fields around solenoids and talking about, well, at least 3 different ways that we could draw a solenoid, and I subtitled it Solenoid Art Show. So we're looking at things like a 2D cross-section way of representing a solenoid, a 3D hose model, a schematic diagram, which is kind of a hybrid of the two. And, before I move on, maybe I should just draw attention to this. I presented this equation once before, but in the center of the solenoid, the magnetic field is strongest. Well, that makes sense. Look at the field lines. They're closest together on the one, at least on the top left there. The other thing that we've said, here's that equation that I was mentioning. B is equal to mu naught N I over L. Now that N is the number of coils. And if I count the ones that I have up here, looks like I've got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. These are all the same solenoid, just drawn 3 different ways, but 4 coils. That would be the N value for that solenoid. So up above, 4 in the diagram above. And if I was looking for the value of mu naught actually was something that we looked at yesterday as well, and I'll sort of slide it on screen. Mu naught, where is it? There it is. 4 pi times 10 to the power of negative 7 Tesla meters per amp. Okay, so that's something that's the magnetic permeability in a vacuum. And so we're going to sort of say that's universal, except for the fact that you're not always in a vacuum. So there you go. Not really universal, I guess. But vacuums are consistent at least. So there's a standard. That's the standard. And then what else could we say about this one? Oh, current. We know what that is. It's just how fast the coulombs are flowing per second. And length. Well, I mean, length is just a physical measurement. So from here to here, use a ruler. That's how long it is, okay? And that would tell us the magnetic field in the center of the solenoid. And of course, magnetic field's going to drop off as we get further and further away from the solenoid, because magnetic fields do that as they get further from their current source. Now, there's a little info box down in the bottom right-hand corner, quick little insight. And I've mentioned a few times in the past week or so, Newton's third law still sort of being something that's in play. And it turns out that if I run a current through a magnetic field, then the current vector and the magnetic field vector will produce a force vector. But it's also true that if I push a wire through a magnetic field and I apply a force vector, then that force vector where I push the wire through that magnetic field will interact with the magnetic field vector and produce a current. And so in that way, a single wire and a horseshoe magnet could be a generator. Okay, so it's almost a reversal, an action-reaction pair reversal. So I kind of want to start thinking about this idea of the reversal, because we've been talking about using current to make magnetic fields and current in a magnetic field to produce force. And I want to think about building this idea of reversing the I don't want to say action reaction, but what's that pair? Consequence and it's not action reaction, it's action and consequence. That's what I was looking for. Action and consequence. So the actions in both of them. So we're going to reverse and think about actions and consequences in a different way. All right, so this, you recognize this already. This is our schematic model for the solenoid. And before we do this, I should ask you guys, again, just as a refresher, why does an AC solenoid hum? I'll put it in quotes. At 60 hertz. Anybody know the answer? Yes. Yeah, this current is switching back and forth at 60 hertz, 60 times per second. But what's happening when the current's flowing? Yeah.
Like the wires push each other away.
Close. They attract.
Yeah.
They attract. So the solenoid contracts when current flows, and then in the crossover points where the current's not flowing, an AC current, it relaxes. So it hums at 60 hertz as a consequence. So yeah, we're sort of piecing these ideas together. The other answer I would have accepted is that AC solenoid hums because it doesn't know the words. All right. Anyway, I won't even put that in writing because it doesn't deserve to be put in writing. But no, I won't put it in writing. I can't. All right. So inducing a current in a solenoid. Let's try it. Now, the interesting thing is we're going to talk about the basics of this, but the unnamed student in the class that produced a radio in her electronics class actually was inducing a current in a solenoid, not by the method that we're talking about, but using electromagnetic waves to induce the current. And that's really how a radio receiver works. But I'm getting ahead of myself, okay? So I don't want to like overcomplicate things. So inducing a current in a solenoid using action-reaction forces. By the way, if I'm inducing a current, that means I don't have to touch the solenoid, but I do have to change something near the solenoid. And so we're talking about here, I'll draw the garden hose model. Antoine de Saint-Exupéry would be so proud of me. All right. And we have this idea that I could take a solenoid and I could shove the north end of my solenoid straight into, I could shove a north end of a magnet straight into a solenoid. I'll label these guys up. Magnet, solenoid. And of course, a solenoid is just a coil of wire. And if I was going to be a little bit better about the 3D drawing here, maybe I'll draw this more like a comic strip. Got my north, I've got my south. For those of us that aren't artistically inclined, let's draw ourselves a toilet paper core. Keep this three-dimensional. We'll have our current coming in, we'll have our wire coming in. Make it nice and simple. We'll just make this be a 3-wrap wire. And here comes the action. So the action is we're going to take this permanent magnet and we're going to force it into the coils of the solenoid. So if I was wrapping my wires around a toilet paper roll or around some cylinder that would keep this thing from collapsing, I could apply a force to this magnet, shoving it in. And what I want to claim is that we can induce a current. Now, if running current through a wire produces a magnetic field, in that situation, the input is the current. The output is the magnetic field. Input, output. Action, reaction, okay? Action, consequence. In this case, the input is shoving a magnetic field into the wire. And so the output is going to be current flow. And there actually is a rule for that. However, you know that if you push a box, doesn't the box resist your push? You know that if you pull on a pulley, the pulley system resists your pull, right? All those things are true. The same thing is true in the electromagnetic realm. If I try to shove in a north into the solenoid, just like a box pushing back on you, produces a reaction magnetic field, and it pushes back on you. So if I try to shove in a north, the solenoid's going to react and say no, and produce its own resistant magnetic field. And what resists an incoming north? I'll hint, it's not a south. It's another north, right? Isn't north repel north? So if I try to shove in a north, it turns out this magnetic field, I'll write it in red, the magnetic field that becomes induced as a reaction to this incoming bar magnet is opposite. It resists the incoming north. And if I take my right-hand rule for solenoids, that means that magnetic field is going to be up north. The current's going to curl around to the right into the page, and you can use your hand to make sure that you get this. That means the current's going to go into the page on the right and come out of the page on the left. And if I follow this around like a labyrinth, that means that the current's going to travel in this direction. And so I say, yeah, I can shove a north into a solenoid and produce current flow. Well, let's draw this again because I want to see if we can change it. Draw my toilet paper roll again. Remember, you got to use your right hand. Don't use your left hand or else it won't work. I'll draw the same coils. So it's the same setup. Okay? Only this time I want to change the input. Last time the input was to shove a north in. This time I want to say same bar magnet, but let's just say it was in there a moment ago and I yank it out. Now the force is this way. I'm pulling my magnet out. Well, what resists a departing north? South. South says, don't go away. Stay where you are. And that happens when I pull a sled too. I try to pull on the sled. The tension in the rope is actually the sled doing, I don't want to, right? It's a resistance. And so we're looking at this reaction thing, kind of an electromagnetic way. And if that's going to be the case, then we're going to put a south pole up here and a north pole down here. But again, I grab my right hand, and my current in this case then is going to follow that right hand rule. The north is pointing down. See my thumb pointing down? That means that my fingers are going to go into the page on the left hand side of that solenoid and wrap around out of the page on the right hand side of that solenoid. And I encourage you, whip out your right hand and make sure that this makes sense to you. Okay? It really is the best way to let it click. The patterns all really are true. Okay? I mean, at this point, you're kind of taking my word for it that it's true. But I got a video, and I can definitely demo it for you. Would you believe that it's not hard to connect an ammeter to a toilet paper roll and shove a magnet in and out? What do you think happens on the ammeter? Look, if I were to draw a dial underneath this one, we'll call it an ammeter, and I put a needle on this thing, would you believe that if there's a positive side and a negative side or something like that, the needle would click this way on the analog ammeter when I push it in? Same analog ammeter. I mean, mine are mostly digital anyway, but it's easier to draw this. If the current goes that way, what way is it going to go when you pull it back out again? Opposite way, right? Now on an analog ammeter, it's just going to have a positive readout and a negative readout, and it'll oscillate back and forth. And this business of 60 hertz, would you believe that if I wanted to have a frequency for my AC, because this is AC current, isn't it? I'm shoving it in, I'm pulling it out. That really is AC current. That's why I brought up the hum thing earlier, right? But if I wanted to have the same frequency of hum on this solenoid, I'd have to be shoving it in and pulling it out 60 times per second. That's fast. I don't think I could do it. You want to know how people do it? They put it on a wheel. I'll build up to the idea. Look at this. If I had the same solenoid, I'll just draw it in miniature for a second. If I took the same solenoid, toilet paper roll. If I took the same solenoid, sure, I could shove it in and out, but would you believe that I could do something similar if I put a magnet on a pendulum, put a north here, and I let this pendulum swing back and forth? You don't actually have to shove the magnet in, as it turns out. All you have to do is let the north approach, because it's the change of the magnetic field that causes this to happen. So if I let the magnet approach but not go in, it works as well. Maybe not as intensely, but it does work, right? Now, the nice thing about just putting it on a pendulum is if I don't have to shove my north in and out, would you believe there's less wear and tear? Less chance of rubbing on the hollow core. So people are like, okay, let's let it swing back and forth. We could have a pendulum generator. And whatever the frequency of the pendulum is would be the number of hertz for that AC current. And we say, okay, well, that's cool, but it kind of seems like we don't want to have a whole bunch of pendulum generators down at Niagara Falls. That seems like not a cool thing for us. In fact, hooking up clocks to the power grid and having pendulums seems a bit silly, but it could work, just not very effectively. And so people say, well, how about we take this pendulum idea and we put, I don't know, like a bunch of magnets on a wheel. And then Here's my solenoid again. Right? And I let this wheel spin. Just let this thing spin around. And of course, that means that the north is going to go towards the mouth of the solenoid sometimes, and it's going to go away from the mouth of the solenoid other times. And when it goes toward, the current's going to go one way. And when it comes away from, the current's going to get yanked the other way. And of course, as I'm drawing this, you imagine like this wouldn't be so hard to set up. I could set up the toilet paper roll on the floor, and I could suspend a bicycle just above this thing. And we could do this. We could mount magnets on the outside hub of a bicycle wheel. You're picturing what I'm saying? In fact, we could even up our game, and we could put one magnet at every spoke of the bicycle wheel. And wouldn't that mean that there are more magnets constantly coming towards and going away from that solenoid? We could spin the wheel as fast as we want. In fact, we could spin the wheel at just the right speed so that a magnet goes past that solenoid 60 times per second. That's something I could regulate. I could put a gear system on there, a pulley system, whatever it is, and I could even hook this wheel up to a waterfall. Basically, this is a paddle wheel system, right? And we haven't gone too far away from the technology that allowed us to grind wheat a few years back when we figured out how to have wheat mills. Like this is still good. Wheels still make things happen, right? And then people say, well, how can I make it even more powerful? Well, I don't want to make it spin faster because I've already got my 60 hertz that I want. So what I could do is mount more solenoids all the way around the hub. And if you've ever seen a turbine generator, I bet you if you see a naked, unhoused turbine generator, you're probably going to see solenoids all the way around the perimeter. And you're probably going to see a wheel with either magnets or electromagnets around the inner wheel. And it's going to be a setup something like this. I mean, mostly you'll see a whole bunch of coils of wire. But really, you're going to see something like this. And the design is such that these magnets are going to zip past the solenoid 60 times per second if it's going to be connected to our electrical grid. If it's just a simple electric motor that's for some other purpose, maybe it's not going to be 60 hertz. But I bet you if it's designed to hook up to our electrical grid, like an electric motor that we're going to plug in to our AC system, it's going to be geared for that frequency of not frequency of rotation, but frequency of magnetic interaction between the inner hub and the outer hub. Am I kind of selling this idea? How many people are buying what I'm selling? Yeah? Okay. All right, so let's put some words on this because I just spoke a lot of stuff, but I feel like we need to put some in writing. So forcing a north pole into a solenoid, let's just say closer to a solenoid. As an action force induces a reaction see how Newton's third law that sounds? Induces a reaction that involves producing an opposite north pole or an oppositional north pole. And I feel that some of you folks would be comfortable with just having this as a textbook reading. But if you read the textbook, this is more or less the same thing that's going to say to you, right? It's just this is kind of like IRL, live action, real time, in the solenoid. And we can say, in turn, this induces current. Induces an associated current. Now, if I stop pushing the magnet, what happens to the current? So I'm pushing this magnet in, and I stop. It's inside, and I just leave it there. What do you think is going to happen to the current? Well, what happens when I pull on a sled with a rope? If I pull on the sled, and then I stop pulling, what happens to the tension in the rope? Doesn't it go slack? No tension, no reaction force, right? Now, if I shove a magnet in and then cease the shove, what's going to happen to the current? I got somebody doing the goose egg symbol. 0, right? It drops to 0. And so I got to keep on shoving in and out if I want to keep current flowing. Or I got to keep that turbine spinning. If I stop the turbine even for a second, the current doesn't flow anymore. It's not like current coasts. It doesn't like coast like a bicycle. It's going downhill. When I stop shoving, the reaction stops, right? So that's why we have these constant turbines spinning down at Niagara Falls. This is why at every nuclear reactor, there's high-speed steam being forced out of the heating chamber that's going to spin our turbines. This is why we have to have spinning blades on wind generators. All these things that spin are doing this thing, right? Now, photoelectric cells, that's different. That is not spinning. But a large number of our electrical resources, even coal power plants, are basically giant kettles that are blowing steam and making things spin, right? Like spinning things, we got this nailed down, okay? I could say this, though, on the other diagram. So this is for the first diagram, pulling a north pole out of a solenoid or away from a solenoid. Away from a solenoid as an action force produces a reaction that involves producing an oppositional south pole. In the solenoid. Right? So we're saying that south poles try to stop north poles from leaving, but it's still an action-reaction. And we can say which in turn produces associated current. All right, so same idea, but going the other way. That's all. And I got a little historical note about Ampere here, and you're welcome to read that on your own time. The electromagnetic molecule, the forerunner of the electron. But like here we are, like mid 1800s, and here we sit in the mid 2000s. Well, not quite, but like maybe 200 years later. And it's crazy to think that these ideas were floating around only just 200 years ago, and all this stuff has given rise to modern electromagnetic telecommunications, all that stuff that we kind of take for granted, Wi-Fi, all based on this stuff, right? Because what I said earlier was we had a student that was talking about making a radio receiver. You notice that I could physically shove a magnet in and out of, doesn't this look like kind of a round antenna thing? I could disturb the current flow in that antenna by shoving a magnet in and out, or I can actually disturb the current flow in that antenna by having a fluctuating magnetic field that's flying through space. Do you know that that's what a radio signal is? It's a fluctuating electromagnetic field that's flying through space. And fluctuating magnetic fields drives current, like we were just saying, right? And so this fluctuating magnetic field at a particular frequency, you guys have probably heard of FM radio. If I modulate the frequency and I send a signal on that frequency carrier, then I can tune it so I can pick up that signal. Now, this particular student did 90 windings. This is obviously a very dumbed down radio, isn't it? This is a one winding radio, but it's just there for illustrative purposes. You guys are you believing in this? So what we're talking about, yes, is about generators, but kind of neat, it's also about radio antennas. But we're not, as a course, we're not going down the radio antenna avenue. I only bring that up because she brought it up, and I think that it's a great connection, okay?